will go away. Yes, yes. And I will go now away from time stepping to full space-time methods. Time stepping is very well known. So I have this illustration on my cover page. This is a space-time cylinder here. So I introduce the notation is always Q, or sometimes I omit this T, say Q. This is the spatial domain, the physical domain, and times the time interval. Capital T is the final time. So omega is always a bounded and Lipschitz continuous subset of RD, a domain in RD. Whereas the space-time cylinder is an RD plus 1, is one dimension higher. So sigma is this here. Wait, sigma is the boundary of the space-time cylinder, where we have boundary condition for the PDEs, parabolic or hyperbolic PDEs. And sigma 0 is the bottom of a space-time cylinder, where the initial conditions are prescribed. And sometimes I need also sigma capital T, this is the top of a space-time cylinder, this one. So this is the space-time cylinder. This is a picture for T is equal to 2. So the space-time cylinder is an R3. And this is a fully unstructured discretization of a space-time cylinder using adaptivity. And this comes from an optimal control problem, by the way. And on this side, you see, and we come back to this, for traditional time stepping. So here we have a traditional time stepping, and here you see the full unstructured space-time discretization, and there's something in between, of course. Okay, the abstract, you know, contents of my lecture, outline of my lecture. After introduction, I will look to some variational formulation. So I will concentrate on parabolic problems. I will look at variational formulation of parabolic initial boundary value problems and their solvability. And usually the different variational formulations are then the starting point for different numerical methods. First, I look at the classical time stepping plus space Galerkin Finite Element discretization. Then the full space-time Finite Element Method, when material for parabolic problems, parabolic optimal control problems, and finally conclusions. So let me start with an introduction. So let's consider a parabolic initial boundary value problem that I can write in for a linear parabolic PDE in this form. So you have one time derivative, and you have an elliptic part, you have a diffusion part, a convection part, a reaction part. Finally, we will concentrate it on a very simple model problem, but everything what we derive can be done for this general problem. At right-hand side is a function f, a source from L2, with a divergence of a vector function. And the vector function can be in L2, so with a distribution. So you will see with an h-1. And then we have boundary conditions. So I only consider here homogeneous Dirichlet after homogenization. You can have this an initial condition. You can also assume that these initial conditions are homogeneous due to homogenization. So when we know that this is a model for a lot of problems, sometimes this equation is called heat equation. So heat conduction and heat transport can be described by this parabolic initial boundary value problem. So with the usual heat capacity, density, and this can be a matrix even, heat conduction matrix. And the right-hand side is usual here, L2, but also another world, electromagnetics, is described for eddy current problems in 2D. In 3D, you have here the curl and the vector equation. In 2D, this is for electrical conductivity and so relativity. And then you have a right-hand side like in 1, namely the current impression F. So this is the third component. And then you have a magnetization. And the magnetization, this is some kind of line distribution. So plus boundary condition, plus initial condition. And the Muffer problem, the model problem that I will consider for simplicity is this one where the elliptic part is the Laplace operator. So I am interested also in this right-hand side because I was working, or I am still working on electromagnetic problem. Okay, this is our really model problem for the presentation. Standard numerical methods, time-stepping methods, of course, and then you can do something first in time, then in space. This is the horizontal method of line, rotor method, or first in space and then in time. This is the vertical method of line, and come back in chapter 3 of my lecture. An alternative method are real space-time method of fully unstructured grid. I will focus on this in chapter 4 and 5. And in between are also some methods I will discuss in a little bit in chapter 3. If we looked at the traditional method and how to overcome some disadvantages. So let us first do some analysis work of parabolic initial boundary value problem, variational formulation, and their solvability. I will present 3 variational formulations. The first one, and Dr. Moore mentioned that I studied in Leningrad, St. Petersburg now, well, my PhD study was there, and Olga Ladyshinskaya was working there, and we celebrated this year in March his 100th birthday. So, and I had lectures by her. So what she was doing, looking at the PDE, by the way, exactly in the general form that I presented, this is from her book, was looking at the PDE. It was multiplying by test function that depend on x and t. So v was depending on x and t. And then she multiplied the PDE by such a test function, used integration by parts in time and in x, here in time, here in x. If you integrate in time, then you have integrals on the bottom, but also on the top. And the bottom, you can insert the initial condition here, and on the top, it is requested that, or is required that, and this means this bar, that the test function is 0, so this integral disappears. So here you use also integration. Now the spaces are anisotropic Sobolev spaces. This means differentiability with respect to x, so the gradient is in L2. This means time derivative. The time derivative is in L2. This means boundary condition, and this means on the top the function is 0 here. So now we do not need for the solution, we do not need time derivative. So this is 0 here. But we need initial condition and boundary condition, and the initial condition is some kind natural. So we end up with this variational formulation. And now some results that you can find in the book by Olga Ladyshinskaya. Assuming that f is in L2 and also this vector function is in L2 with all components, and the initial condition is also in L2. So we have no compatibility between boundary 0 and initial conditions. And then she proved in the general case, so imposing conditions on the coefficients, I will not discuss this, existence and uniqueness. when she already saw that the solution U is better than described by the space, namely, she observed, so I write it now already in a language of Bochner spaces, that the T trace is continuous with respect to L2 norm. And then initial conditions make sense in L2. So you can go, you see the initial condition in L2. So this was denoted with V. This is the notation from Olga Ladyshinskaya. So this is an inbuilt regularity. It's better. And what is also important for me here, or we'll see it later, if we assume compatibility of an initial condition with a boundary condition, so there are zero, so then it must be an H1. Otherwise, I cannot speak about boundary conditions or boundary values of initial values. So U0 is not only in L2, but in H10. So this 0 means 0 on the boundary. At the right-hand side is an L2. So say this vector function is 0. The right-hand side is an L2. Then the solution, okay, we know this is in this space, but additionally is in this space. And this means W delta means that the Laplace operator of U is in L2, and the time derivatives are now also in L2. And we have some continuity in the sense not only L2, but in H1. So the initial conditions are, you see the initial condition with the classes of H1, right? And this is called nowadays maximal parabolic regularity. And afterward, Lyons asked how to formulate conditions imposed on the coefficients such that we have maximal parabolic regularity. So maximal parabolic regularity means this. And finally, it means if this is an L2 and this is L2, and the right-hand side is an L2, then the PDE can be written in some strong sense of L2. Laplace in L2 not means that we have second order derivatives in space that are in L2. We can have singularities in the first order derivatives in the gradient. So the proof idea is interesting because it leads to the vertical method of lines. So she took some ordinal system in H1, 0. So it exists a parabol space. Then we look for the solution in form of a linear combination with coefficient depending on t. When this is inserted in the variational formulation above in 2, when you see, you get an ODE system in order to define these coefficients. And then ODE system, you know, there is the famous lemma Picard-Lindelöf. So you have existence uniqueness. When you have an a priori estimate, this is bounded. When you have, there exists in U that this sequence will weakly converge to this U, and then you can show this is the solution. So this is a very powerful proof tool that can be applied also to nonlinear problems. It's the usual tool you use. So, okay, this is the first approach. When I coming to the line variational formulation, you can find it in Leon's Matchiness and Zeidler, the books of Zeidler also. And here the idea was a line variational formulation to multiply the PDE by a test function that is only depending on x. When you integrate by parts only, of course, only in the elliptic part and here in the divergence right-hand side, and end up with this variational formulation. Line means line is t for almost all t. If I write here tot, this means not for all, but for almost all t. So this is a bilinear form now as an elliptic case. So in general, it can depend on t. If the coefficients depend on t, this is called autonomous parabolic problem, which generates you an operator mapping v mapping this space to v star. And yeah, I have to write something here. This is in fact not the write for L2 integral is not correct. You have to write the duality product. So if I write the L2 integral, please always understand this as a duality product. But this duality product is the extension of L2 inner product. So that means that the time derivative belongs to the adjoint space here. So the time derivative belongs to the adjoint space. This is h, L2 0t, h minus 1 omega. Okay. So then I can write this for almost all t in this adjoint space. Or if I take this space, I have an operator ODE in the space L2 0t v star. Okay, and you can add initial condition in L2, H is L2. So, okay, you see already here a very general framework that can be used. Even this operator can be nonlinear. You can investigate and can derive results with the technique that I show. And this is a theorem you find in Zeitler's. Yeah, it must be a Gelfand triple. This is a Gelfand triple, H10, L2, H minus 1, v star. When you need the boundness of a bilinear form coming from the elliptic part, this one here, this is clear for almost all t. If t dependent, in my case, it's not t dependent. And then you need ellipticity. By the way, this is not needed, because there's always a so-called, I call it E-trick. So if you make the transformation, you can always obtain, also if you have a big convection part, you can obtain such a estimate after this transformation. So we can assume this from the very beginning. And the right-hand side is clear, it must be in the adjoint, in the dual space. Initial condition in H means in L2. So this is already an abstract framework. When you have existence and uniqueness in this space, Leon's called it W0T space, such that the line variational formulation is valid. The same technique for the proof. You find it, for instance, in Zeitler's book. So now I come to something else. Space-time variational formulation in Bochner spaces. So I multiply the parabolic PDE by a test function that depends also on t, on x and t, as an addition square case. Multiply, but again, I do not partial integration in t here. So when it's again from the dual space here, this one. So, but now I have the following spaces. The space x0 is H10, 10 TVH space as before, but I incorporate the initial condition in the space. You know, Ladyshinsky used integration by parts, and the initial condition was some kind of natural condition at the bottom of the space-time cylinder. Okay, now it's in the space. And then I end up with this. Now the operator is operator A is given from x0 to y star. So I can here write, this is space, this is in the Bochner spaces now. Now I have here y star, y, not v star, v for almost all t. No, y star y. Okay, this can I write as a bilinear form again? So this is this one, but correctly written this one. The bilinear form generates operator mapping x0 to y star. So I end up again with an operator equation. So I look for mu in x0 in this space, where the initial conditions are incorporated as essential conditions. The boundary condition also, boundary conditions are here, such that Bu is equal to F in the dual space of Y. So, and now I can use another technique. This is the famous Babushka-Necas or Banach-Necas-Babushka theorem. And the theorem says B as an operator from x0 to y star is an isomorphism. That means it's bijective. B is bounded or continuous, and the inverse is also bounded and continuous. So this was proven by Olaf Steinbach. And what Banach-Necas, famous Banach-Necas theorem says, within an ISO, if and only if the following three conditions are fulfilled. B is bounded, this is easy. The bilinear form B is bounded, Cauchy, and then you have it. So when so this is easy. For in subcondition, Olaf Steinbach could be proved with a factor 2 here, by the way, so this is not necessary. This is for in subcondition for the bilinear form. So we can estimate the supremum, taking the supremum over this test function from below by the norm of u in x with a positive constant for all u. The norm in x is the norm of u in y, and the norm of the derivative in y star. And the norm in y is nothing else than the L2 norm of a gradient. Excuse me. Of a gradient. So here, by the way, in the proof, we use the least representation in y of a time derivative. So dual norm has always a representation in the y norm. I will not give a proof here. I will prove a discrete. This is more important. The discrete in subcondition. The discrete in subcondition does not follow from within subcondition, of course, but the proof technique is almost the same, I have to say, almost the same. And then we need a third condition that says that for all v from y, there exists a u from our x0 star, where we look for the solution, such that buv is not 0. So how to prove this? You take y, and then you have to construct the u, right? And you take this, you integrate from 0 bis t, and then you have a time derivative. So this is x0. The boundary conditions are also fulfilled. So this integral from 0 to t, y, is in x0. And now you insert this, and here you have a proof. I will not go through the proof. This is our 2 lines. This is an exercise. This is positive. So because this part, you see, if you take the derivative, you have v, and so you get that this, and this is a non-negative part. Okay, all 3 conditions are fulfilled. So B is an ISO. This is the best what you can expect, and you have a constants. You have all constants. Also the constants of a bilinear form here is also a square root of 2, the boundedness constant for the Laplace operator, of course. So by side, yeah, when you have an estimate, because you have an a priori estimate, because you have an estimate of an inverse operator, of a norm of inverse operator, you have a priori estimates. So I did not write down the a priori estimates. So the norm of B is bounded by this square root of 2, and the norm of B minus 1 is bounded by also square root of 2. 1 over the in subcondition. Okay. So summarizing, I present to you three variational formulation, addition scale with integration by parts in T, the line variational formulation, and the space-time variational formulation. So in different proofs, and here proof with Banach-Necas-Babushka theory. Now I come to time stepping. So I have to look at the time stepping. I think I can do it very fast. So starting point is the line variational formulation, of course. And then we have two possibilities. First in time, then in space. This is called horizontal method of lines, or Rode's method. Rode's invent this method in order to prove analytic results. And you can do it as well. So first in time, let us look only in implicit Euler. So we discretize the space-time intervals in subintervals. Here of a same length tau, but you can do a non-uniform decomposition of a space-time interval. And then you consider your variational formulation at t j plus 1 and replace the time derivative here by the backward difference. So the value at the time j plus 1 minus uj over the time step. So this is an approximation of the time derivative. Okay, and here is a backward, and here you have the time for implicit Euler at t j plus 1. Okay, and if you look to this and bring this to the other side, then you see that this generates an elliptic equation. So uj plus 1 is the solution of elliptic boundary value problem. So with a bilinear form aj plus 1, this comes from the elliptic bilinear form and from the time discretization that we have h is always L2. So this goes to the right hand side, the new right hand side. So you have to solve, you have to solve at each time step an elliptic equation. Of course, you can use finite element method, isogeometric analysis, what you want. And what you can here use, you can also use adaptive methods. At each time step, you can use another adaptive approach. So this makes this approach interesting for people who want to solve a problem with an adaptive finite element method. But here we look on the simple finite element method. So we look for an approximate solution in a finite element space. So VH should be a subspace of V spanned by, say, head function. We have a discretization of your domain omega, the special domain omega, and then you can use basically your elliptic code if you want and look for an approximation. This is equivalent to the solution of linear equation where the matrix is a stiffness matrix plus 1 over tau of a mass matrix. So you generate the matrix, you solve the system, then you have a coefficient in this linear combination, and then you have this approximation. So this is the first method. So here, mass matrix, stiffness matrix, you see. Then the vertical method in line, and this is usually the standard method you find in the books, in the lecture notes. So first space. So you use the finite element with time-dependent coefficient. So in the elliptic case, you have this one, and now the coefficients are time-dependent. It's the same idea as in the proof of existence and uniqueness. You remember, this was an orthonormal system. Now I use the head function, something like this, finite element basis function. So when you can incorporate, also easily incorporate inhomogeneous boundary conditions. So here, no, this is a zero homogeneous. I take this away. So when I need to define the coefficient, very easy, I insert this to our line variational formulation. Then here you have a time derivative, and test this with, as usual, as an elliptic case, with basis function. Here you can extract this, and what you see is nothing else than a large ODE system. This gives the mass matrix here. This is now the vector with all coefficients. With all coefficients should be from H1. So the dot here means the time derivative. So this is the stiffness matrix here. And the initial condition, you use the L2 projection of a given initial conditions. So then you have to solve this ODE system. And we do it by some Runge-Kutta method. So the so-called family of theta method are very popular. So Crank-Nicholson and implicit Euler are the most important one, because this is, of course, a stiff system due to the eigenvalue m-1k has a condition number h-2. So this is explicit Euler is only conditional stable. So unconditional stable methods are for implicit Euler and Crank-Nicholson. For instance, implicit Euler. Now, formally, I get the same as before. So we have to solve the system again, okay, as you see. But the difference of these two approaches is here you cannot apply an additive method because the discretization is given in advance. So you have one mesh, you have your basis function, and you make this ansatz. It's not possible to use an additive method that is changing in time. If you use this approach, you can do easily this here. So you can do easily an adaptive. The people invented the discrete Galerkin methods in time when you can change the discretization and have only this method. Many cores. Then, of course, this time-stepping method is other time integration methods, all the same, Nicholson, the theta family. Then this is a time-stepping method. This is a sequential method to time, sequential time-stepping. You start with the initial condition, then you compute U1 at the first time step, then U2, and so on and so forth, solving this system. This is not good for parallelization. And when the people were thinking about parallel method in time, parallel method in time, and the crazy idea is you look to the system. So you have always this piece. If you write all this equation all at once, you have the piece as a big system. You can do this, of course. Then you have on the diagonal this, and on the subdiagonal, if you bring this to the other side, minus m. Of course, as usual, you start with U0 is given, then define U1, solving the system P1, U1, this right-hand side, in a time-stepping approach, but this is not good. So now you do the crazy thing, you look at this big system and use a method for solving this big system all at once. For instance, the multicrit method. So there's a nice paper by Gander and Neumüller, but the people started it long time ago in connection with ODEs, by the way. With PDEs, for instance, Wolfgang Hackbusch proposed a method in 1984 or 5 for solving this system by a multicrit method. And we did Gander and Neumüller did this also by multicrit methods. So there was a nice survey article by Martin Gander, this was 2015, 50 years of time parallel time integration. So, and another one also having this gap to 2020 application of time parallelization. So Ong and Schroeder. So now I come to my main thing with the space-time finite element method for parabolic equation. Okay, I want to discretize the whole space-time cylinder. The whole space-time cylinder, and I do it like an elliptic case. I decompose the space-time cylinder into simplicial elements. Say. This is t is equal to 2, so space-time cylinder is three-dimensional, as here you decompose into simplicial elements. And when I use subspaces of my variational spaces, I use in the variational formulation, where I look for the solution. This was x0, this is now x0h, this was y, this is yh for the test function. They should have same dimension. In principle, you can use a Petrov-Galerkin technique, different spaces, but here I look, as Olaf Steinbach did, the case that we use the same space for trial function and test functions. Namely, the usual space, you know, from the elliptic case, the SHKQ on the decomposition tau. So we have a decomposition tau in the limtices, and we define continuous spaces, piecewise polynomials of a degree k. So this is degree k. And intersect with zero means prescribe the boundary condition and the initial condition. So this is the regular case. So I do not explain now the regular case. You can do it in different way. I always do it with, if you have a mapping, here an affine linear mapping from the master element. I do it in the lecture. From the master element of the element in the decomposition, and then you request the usual things for the determinant, for the modulus of a determinant, and for the spectral norm of a determinant, of a Jacobian. And the same is true for nonlinear mappings. So this is a regular decomposition, quasi-uniform, sometimes called. So all the local H deltas, the local mesh size, can be bounded by a global from above and below. So from above you can use a maximum, and here you have a local thing. So under this condition, one can prove suitable quasi-interpolation. Let us consider this one. Area estimate, for instance, Banach-Scott. In the H1 norm, in the L2 norm, H1 norm looks like this. This is like in a class book. If you have sufficient regularity, hk plus 1, then you have here hk. Okay, space-time finite element method. We have our variational formulation now. We have existence and uniqueness. It looks like here like an elliptic problem, but it's a parabolic problem. And now I use for finite element ansatz like an elliptic. So we integrate over space-time cylinder. The coefficient depends on nothing, not on t, nothing. Pi depends on x and t. This the Pi depends on x and t. So now I look for the solution in my finite element space such that, as usual, the variational formulation is fulfilled for all test functions. So this space and this space are the same. It's enough they have the same dimension. Again, we have a question of existence and uniqueness and error estimates. This is clear. I will come back to this. Okay, you can generate with this bilinear form your stiffness matrix, your right-hand side, solve the system. If it's solvable, fine, and then you have a solution. You solve one system always, but a huge one. So for existence and uniqueness, we need the discrete in subcondition, and of course, which will not follow from the in subcondition in the infinite dimensional setting. Okay, this is the first one. The second one is we try to prove this in subcondition. This would be the exact counterpart of the in subcondition. So I add here h with a norm x here, or x0. Use the same norm. But we could not prove this. But we replace this by discrete norm and come back to this norm, and then we could prove this. Then, of course, if this is a norm, then you have existence and uniqueness. So we replaced this norm by this norm. So open question is this also for this norm. What is this norm? Is discrete norm xh is the norm of y as usual. And here we would have the norm of a time derivative of u in y star. And what we are doing, we use again the discrete Ries representation. We solve such a problem. So u is given, then you solve a finite element problem, a discrete problem, and you get the discrete representation. This is inserted here, and not w, where you solve for the full space. So, okay, this is a discrete norm. This is the place where we use this discrete norm. Okay, this can be estimated by the full norm from, unfortunately, only from above. If from below, when we are done, but from above. Because this norm, as you can see here, you insert this, and then you can go to this, and then you use the estimate by the dual and by the norm. This is a dual is a representation of W. So this cancels out, and then you have a representation of a discrete norm, of a Y norm of a discrete finite element Ries representation. This representation. Okay. So fine. Let's now prove with modified discrete in subcondition. You can do the same for the infinite dimensional in subcondition. So what you have to do for some u, you have to find a v, and then you have an estimate from below. So for every fixed u, we have to find a v. So, and what we take for the v is UH, here UH, plus WH. And WH is here, again, Ries representation in the finite element space. In the finite element space. In the infinite dimensional in subcondition, you need the Ries representation without this H, so in the full space, and can do the same. So let's assume that for a given UH, we take this, when we have an estimate from below, and we can estimate, so the numerator from below, so here we have UH, we see this, and this, and this. 2 to 5 to this is nothing else as AWH, WH. This is the norm, this is also the Y norm, and this also by 5, we have the time derivative of UH. So this can be written as, the usual trick integral from 0, the derivative of a squared, and then you can integrate in t, and you end up with this one. This is a simple exercise, because you know that this product can be always represented as something like this. So when you have a proof. So when you can estimate this from, so this is non-negative, so you can estimate this from by this, and this is the discrete norm. And on the other hand, you can estimate the denominator now from above using triangle inequality. And here use again Cauchy inequality, f is square root of 2. And we are done. So this was the discrete in subcondition, the same way you do the infinite discrete in subcondition. So what does this mean? The discrete in subcondition mean that the kernel of your matrix is only for 0, as you see here. We have a representation. This is a norm. This is 0. When this is 0. So the matrix is regular. So you have existence and uniqueness. what I have here. So we have a unique solution. Moreover, we see that BUH is positive if UH is not 0. So if a matrix is positive definite, by the way. And the third condition from BNB, this follows from the, is not necessary, it's not important here, but this follows from the condition. Okay, now we have a CR-like lemma. We have existence uniqueness, and we have an estimate of a discretization error by the best approximation error. So by the best approximation error, but here, to the discrete in subcondition is only in this XH and not X. We have a space, we have a discrete norm. This consists on the Y norm plus the discrete norm for the time derivative using the Ries representation. And the factor is 3. So the proof, I will jump due to the time, I will jump. The proof is very easy. Using the using usual thing, you insert an arbitrary function here, use triangle inequality, and then here you use a discrete in subcondition, Galerkin orthogonality, and then you have it. So convergence rate estimate, you insert now here, so you have a best approximation estimate, you insert here now an interpolant of u. Lagrange, if a function is smooth, if u is continuous, you can use Lagrange, pointwise interpolation, or if not, you can use it only in L2, you can use Clermont and Scott and Zhang, if you, for instance, a time derivative only in L2. If you insert this, when I make a very quick estimate now, this is not the best one you can do, and the red dots show where one can improve a thing. So what you see that this norm is this part and this in the adjoint. So this part, this is only the x gradient of the interpolation error. I estimate this by the full gradient, by the H1 norm. So of course, here you can do possibly better. And of course, when we have the interpolation, quasi-interpolation error estimate, if you have a little bit regularity, more than H1, then we have this. In the dual norm, the same game, we have this representation. We now know from the regularity that the time derivative should at least in L2. When we have this representation, then we can estimate by the L2 norm, and this here we have a gradient of a L2 norm, x gradient. This is already enough to have some kind of Friedrich inequality. This is enough in space. And then you have here for supremum is gone. You have now only the time derivative of the interpolation error. And again, I make this overestimation maybe with H1 interpolation error and get the same. So finally, I have this. At least one first estimate. If you have a little bit more regularity than H2, then we have H to something as an elliptic case. Now, since I did this work with Stephen Moore, so in the PhD thesis, Upwind scheme for IGA even. Upwind space-time finite element discretization. The starting point is maximal parabolic regularity. You must have maximal parabolic regularity. Then you can write the PDE in L2. So we have to assume that this guy is in L2 or 0. So when we have a PDE in L2, we have a boundary condition, we have initial conditions should be also in H10, not in L2. And then we can look to this as an elliptic problem with an upwind in time. And then we know, okay, when we should use an upwind stabilization using here the time derivative. If you have a convection problem, then you should add also the derivatives from the space. And this function is basically h squared here. This is a mesh density, in general, is a mesh density function. If you do this and use integration by parts in the elliptic part only, again, you end up with a discrete bilinear form, because here in the test function, you have a h involved, and in the discrete linear functional, because here you have also this h involved, basically. So, but this is a finite element scheme. So I look for the same UH in the same space x0h, such that this is fulfilled for all test functions. So, and now there are 5 points and we have everything. This is maybe more easier. We have immediately consistency because you have this one. This follows immediately from here. You have consistency. This is a consistent scheme. If you subtract this, I have to do this here from this, then you have Galerkin orthogonality. Super. And then you have to show ellipticity of a bilinear form, but you can do this here, but in the discrete norm. The discrete norm is, if you look at the bilinear form, then you see all positive, symmetric and positive terms define you the discrete norm. All the other terms, something like this here, coming from this, with a space derivative, you have to use the inverse inequality. But you can do this. This has a positive constant. Can estimate this from below. You have to show boundedness, but not on the space in the first variable, not in the space x0h from the test space, yes, but you have to take into account the solution space. And the solution space is this, h delta 1. And then you can show a CR-like estimate in this norm that takes care of this delta. This is an extended norm that controls L2 norms by the way as well. So having this, we have again the rate estimate here, and I wrote a little bit another. So S is a regularity here, so minimum S and K are the degree of basis function, polynomial degree, and S larger than 1. A little bit regularity is enough. So there are classical paper of this SOPG, streamline diffusion, Galerkin squares by Johnson, by Hughes in the 80s, using also this technique on time slices. So we did this with Stephen was PhD thesis with IGA, space-time IGA. And recently with Andreas Schaffelner, we did this also if we have a right-hand side that is distributional. This seems is not possible, but is possible if you know that at least on some subdomains, magnets, this divergence is an L2, but can have jump over across the subdomains. Then you can do it as well. Numerical example, so I will then skip well, at least one numerical example where we have here a coefficient. I say for simplicity, no coefficient. Here I have a coefficient, even a coefficient that depends on t and x. So this is a non-autonomous case. So this is an interface. So computational domain here is 2-dimensional, and the interface is running from here to here. So it's moving. So if you move from here to here, you see that the interface is running. But in the space-time cylinder, the interface is fixed. So if we have large coefficient jumps like in an electrical machine, we think on an electrical machine, and did also already computation with this, but here this is easier. And for this, by the way, you can also show maximal parabolic regularity. The coefficient should have almost everywhere in X, should be bounded variation in T. This is the case here, obviously. When there are very new results, you have maximal parabolic regularity. So we are on a solid basis here. So you can start here. So this is now such an Upwind scheme. And here you can see for t is equal to 2. So here we have t is equal to 2. So t plus 1, t is equal to 2, t is equal to 3. This is a 3-dimensional space-time cylinder. This is a 4-dimensional space-time cylinder. And here you see for linear basis function, quadratic basis function, and cubic basis function, and you come to the optimal rate if you use uniform refinement. What we want. Here it looks a bit, you have also optimal rate, but this is due to bisection. Here we use the usual uniform refinement of tetraedrons. Here we use the bisection of pentagons. Okay, also I copied for the space 2-dimensional case for computational time. So this could be solved, these problems, using here you have AMG Y cycle, preconditioned flexible GMRS solver. It's not symmetric for problem. Here with the AMG Y cycle, here with the so-called AMNI cycle, I cannot explain, with a cooperation with Banach-Necas-Babushka. At least you can solve a big problem with about 350,000 unknowns in something like 2 seconds. And then we did the same in 40, 250,000 less than 1 second. So you can do it fast if you use parallel computer, of course. This is the number of cores that you see on quartz in Livermore. So I think we have not enough time to go to the optimal control problem or very fast. The optimal control problem, especially space-time tracking problems, are very suited because in an optimality system, so it looks like this used for state equation and used for the control. Control is the right-hand side for source here. So here we want to have a space-time control. We want to track a given desired state or given target, and we want to find, say, a temperature that is very close to this given temperature, something like this. So we have to regularize this. We use L2 regularization as usual. It's very standard. Lambda is the regularization parameter. When this is, when one can easily prove existence and uniqueness using the solution operator, then it's quadratic minimization problem. And this is equivalent to the optimality system. For the optimality system, you need the co-state, the Lagrange multipliers, because there's a constraint here. So that can be written in the same variational setting. The state has initial condition, the co-state has conditions on the final state, so 0 on the final state. This means the xt. So we look for the solution of the system, this is equivalent to the optimal control problem, and you can easily prove we are in the setting of maximal parabolic regularity here. So it's really true that this is the reduced optimality system, reduced by the gradient equation here, by the way. We have these two equations forward in time, L2, it's valid in L2, and backward, we have a minus here, but in the well-posed sense, in time for the co-state. So then you can solve with a Galerkin method. So you have the same bilinear form, or with an upwind and downwind method. So here you need an upwind test function. Here you need a downwind test function, of course. When you have a discrete bilinear form, you can prove, again, everything, existence, uniqueness here, existence and uniqueness here. You can derive discretization error estimate in different norms. So here we have this discrete norm. Here we have this Y norm only, by the way. So this is a stronger norm, of course. Okay, numerical results very fast. You have a ball that starts expand and then shrink. Here you see for different times. That means in the space-time cylinder, the target is the target. In the space-time cylinder, the target is a ball fixed, of course. in space. This comes up, pops up, blows up, and then shrinks. We use adaptivity here in space-time adaptivity. This is a big advantage. You see this here for duty results. We do not know for solution, but we use for indicators, for error indicators here, and look at the decay of the error indicators. And we have optimal rates, observed optimal rates for linear, quadratic, and cubic elements, h squared, h to the power 3. So now I come to the conclusion. I owe my time a little bit. Conclusion. Unstructured space-time methods, as I discussed in the last chapters, have a great potential, in my opinion, with respect to what? Adaptivity. Here we have really adaptivity, space-time adaptivity. With tetraders, these are cuts only, time cuts. And sometimes after triangle in the time cuts, not so nice, but since this is not important, it's only visualization. But in the 4D, they are shape regular. We have optimal rates here. So adaptivity is simultaneous space-time adaptivity is really a nice thing here. Time stepping, you know, we have, it's not so easy. To solve this problem is not so easy. You need to move the meshes and everything, or cut them or something like this. Parallelization. You solve this problem always in parallel. So we have also the strong and weak scaling studies. Parallelization is easy, like an elliptic. You use methods, distribute for here not for triangles, but tetrahedrons, distribute the tetrahedrons, and then solve. Treatment of moving interface and domains easy. One example I showed to you, because they're fixed. You can approximate. If you do not, if you have such an interface as I show you here, and you do not really always approximate the interface, when you lose convergence rate. Here not, of course not. So optimal control problems are suited for optimal control problems. Anyway, you have a forward and a backward problem, and you, especially if you need tracking problems all the time. Shape and topology optimization. So one of my former PhD students gave a very nice talk now on shape and topology optimization for electrical machines using space-time technique. Stochastic PDEs, SPDs, and many more. So references. So I am working for CAUST, I am working on the lecture notes. So this is in preparation. I can then also provide with this lecture notes where you can find this material with all proofs and all things. And I want to show also this collection of articles, of survey articles that we collected. That means Olaf Steinbach and I collected after a special semester at RICAM. And in particular, Olaf Steinbach and Hui Dong-Yang wrote a survey article on these space-time, not on parallel in time method, but on these space-time method. And at least until 2000, I would say 17, you find everything, literature overview also here in this book. So thank you very much for your attention. I am looking forward to your questions.
Thank you very, very much.